I'll get us started here. Thanks everybody for joining the Conservation Sciences Seminar Series for fall of 2021. Today we have Dr. Leif Olmanson from Forest Resources. So just like housekeeping a little bit, feel free to ask questions in the chat box throughout the presentation, or feel free to unmute yourselves after the presentation and ask Dr. Olmanson directly. So Leif Olmanson is a researcher at the University of Minnesota with over 20 years experience developing remote sensing applications to create temporally and spatially rigorous data sets of water and land resources for large area ecosystem characterization. He's particularly interested in developing field validated image processing methods implemented in automated geospatial analysis systems, such as Google's Earth Engine and Minnesota Supercomputing Institute's supercomputers, to gain a better understanding of the natural environment. He currently leads a team of researchers and computer scientists to build a system capable of near real-time water quality monitoring for Minnesota's greater than 10,000 lakes using satellite imagery. And this provides critical water quality information for lake and fisheries management. So with that, I will turn it over to Dr. Olmanson and start the presentation.
Okay, so let's see. So you see my screen now?
I do not see it now.
Okay. I'm gonna give you a little bit of background on what we've
Sorry, I do not see it now.
Oh, you don't see it yet?
Yes.
Do you see it now, or? Oh, here. How's that?
Yep, sweet.
Okay, you got it. Cool. Okay. I'm gonna give you a little bit of background on what we've done in the past, and then I'm gonna move into some of the work we've been doing using satellite remote sensing for automated image processing for lake water quality. And that was with the help of David Porter of the Minnesota Supercomputing Institute. So first, I'm just going to give you an idea for why Minnesota's been a really good place to do this. And we got the Lagos data here set on the left. They just compiled all the data that was available in this area. And as you can see from that, Minnesota was an earlier adopter of collecting water quality data, and they continue to this day have a lot of data to work with. So that has been real helpful because there's lots of parts of the world, other people that are doing this kind of research where field measurements are very limiting and lacking. With the other side over here with the chlorophyll, this is a cyan project. This is the chlorophyll data that was in 3 days of a Sentinel-2 image. And as you can see on that, Minnesota is well represented in that data set for our continental project. Let's see, so what we've been doing, we have lots of field measurements. So we've been taking the data. We started out with just the second data that the systems were collecting in Minnesota. At the same time, the satellites were collecting imagery. So what we do is we find good, clear imagery from late summer index periods, or looking kind of like the dog days of summer, linking that up with the field data within a few days of the image, build a statistical model of the relationship, apply that back to all lakes on an image, do that for enough images, we come up with the water clarity for the whole state. So using that methodology, we completed 9 statewide assessments since 1975. This included over 10,000 lakes, and we did that at around 5-year intervals due to the image processing it would take, and then the available imagery was a little bit more lacking in the past. And we used for analysis spatial and temporal trends and causal factors, and I'll give you a little bit of background on some of the stuff I've been working on that. I'm not quite finished with it, but give you some updates on that stuff too. One thing we did back in 2001 is we made all this data available in the Lake browser. Some of you may have seen it. It's basically an online resource where people can get information about their lakes. And it's been real popular with thousands of unique visitors coming monthly to get information. Having the data at 5-year intervals has been great. but really if we want to improve lake and fisheries management, we need more water quality variable more often, and that's where we're going with these new satellite systems that have been available recently. We have higher spatial, spectral, radiometric, and temporal resolution. So not only can we map water clarity, but we can also map the components that contribute to water clarity, things like the chlorophyll in the water, suspended materials, and then the color dissolved organic matter. So the way we have 2 satellites that are available. We have Landsat 8 and then Sentinel 2. Basically the spectral characteristics are what determine how well it can measure different water quality variables. And so I have all the spectral bands on the bottom of this graph here. And then I have some characteristic reflectance spectra, which were collected in Minnesota lakes. So if we have just clear water, we're gonna have this peak at around 550, the blue one here. Once we get chlorophyll in the water, we're gonna have a big peak at around 705, the red edge band. And then we're gonna have a absorption trough around 670. That's due to the photosynthesis of the chlorophyll. And then if we have a cyanobacteria, we're gonna have this another dip at around 620. Let's see, and then if you have CDOM in the water, if you have CDOM, brown stuff in water, if you're looking at this brown one over here, you're gonna have this very flat signal. If there's no chlorophyll in the water, you're just gonna have nothing in there. If you have chlorophyll and a lot of CDOM, you're gonna have like this yellow. So CDOM is very absorbing in the shorter wavelength, and that decreases as the wavelengths get longer. And you can see the comparison of the yellow one to the red one or the green one to see how it pulls the shorter wavelengths down, but leaves the longer wavelengths pretty intact. So it still allows us to measure chlorophyll even in these high CDOM waters. If you note the water, so like ocean water, just keep in mind, the models that ocean are using are a blue and a green band here, and you can see how that would be kind of messed up in with our CDOM dominated lakes. Most of our lakes have some CDOM in them, and some of them have a lot of CDOM in them. Okay, so we have the characteristics for the satellites. I can see the Landsat, which has been around since the 70s. The Landsat TM was the first one with this band set, and that was in the 84, 85. Basically we have kind of limited band set. We do not have that red edge band. Big advantage came when the Sentinel-2 came in with this red edge band here. And then if you really want a nice band set, we have Sentinel-3. Sentinel-3 is 300 kilometers, whereas the Sentinel-2 is 20. For all the interested useful bands, and the Landsat is 30 meters. So the Sentinel-3 is great for larger lakes. So maybe 900 lakes in Minnesota can be assessed with that sensor. So we're more interested in all the lakes. So we've been really concentrating on Sentinel-2 and Landsat for this. Another big advantage of the Sentinel-2 is the high temporal resolution, whereas Landsat 8's been every 16 days. The Sentinel-2 is every 5 days, and with the overlap every 2 to 3 days. There is an additional Landsat satellite, which we launched next Monday, actually. And hopefully everything goes well. And then there'll be 2 of that type of sensor, similar to the Landsat 8. So there's not any real advancement except for the thermal band is a better thermal sensor, which is a big advantage for the Landsat sensor. Okay, so with this temporal coverage, I'll just give you a little video of showing the Sentinel-2A and then Sentinel-2B. You can see how they're collecting imagery, and they just kind of keep going to cover the whole planet within 5 days, which is a very great accomplishment. And one of the probably the biggest things is with the remote sensing of moderate resolution or moderate sized lakes. How's that translating to what we see in Minnesota? So one thing you'll notice is there's a lot of cloud cover in Minnesota for most of this imagery. Most of these would not be included for the manual techniques I used before because it's just too hard to get rid of all the artifacts that are in there. That one might be okay and a part of that one, but most of them would be not very useful. So we really need a better way of doing this. We have a lot of imagery now, and so we need better tools to be able to work with that. We have shown this is the Landsat now. You can see the difference here. Oops, wrong way. No overlaps from one image to the next, and so quite a lot smaller width of the imagery, and then a lot fewer of them with the temporal coverage. But doubling that and having the thermal sensor, the Landsat is also a usable sensor. What we've been using it for, it works really well for the color dissolved organic matter and for water clarity, and it's not as good for the chlorophyll because not having that lack of that red edge band. Okay, so to make best use of this imagery, we've have a collaborative effort between the Water Research Center and the Minnesota Supercomputing Institute and the Department of Forest Resources. Basically, we're taking this opportunity. We built a near real-time water quality monitoring system. We currently do not have it operating near real time, but we have the capability to do that if the resources are there to support it. It's just that every time you process the imagery, it takes about the same time to process every week as it does to process the whole summer. So you really need a use case to be able to fund that. So we have all this new satellite imagery. It's downloaded to the ground stations. There we can do machine-to-machine access right into the Minnesota Supercomputing Institute. And then that's where the fun begins with getting the imagery ready to work with. It's a lot of pre-processing, atmospheric correction, and then masking off affected pixels that would give us erroneous results. So this is where most of our work is. Here's an example of atmospheric correction. So basically, atmospheric correction is basically removing the effects from the atmosphere from the images that typically changes from day to day. And so that's very important for building a normalized product that we can apply, we can develop a model for, and then apply all of the same model to all of the atmospherically corrected images instead of having to calibrate each one individually with field measurements within a few days, which would not work for our automated system. Okay, so atmospheric correction is basically correcting to what you expect on the ground. And so we're going from this signal top of atmosphere, and then this is what we would be expecting. And that works great. There's lots of atmospheric corrections out there for water. And I've been testing a lot of them, and they all give different results. Some work better than others, but they're not consistent. So you can't just use one atmospheric correction and then apply somebody else's algorithm. You need to actually calibrate them to the atmospheric correction because you will get different results with that. The other big thing is cloud masking. It's really important to get rid of the artifacts from the imagery. What we've been found to work fairly well was we started with the FMAS 4, which is a available cloud mask. And if you just use that, it includes a lot of artifacts around the edges of where the clouds and shadows would be. And so we basically just buffered that a little bit. And then we had to do some more additional masking for haze over water and aquatic vegetation and other bottom effects. So a few extra masks besides just the off-the-shelf cloud mask that works fairly well for terrestrial features. The thing with the water is it's a very low signal compared to vegetation. So that needs a lot. It's more important to have good atmospheric correction with water than it is with land. So here's our first at doing in the middle here is doing haze vegetation mask, cloud shadow mask. And what we found was we had some anomalies showing up, and it turned out that the anomalies were due to wildfire smoke. We've been getting a lot of wildfire smoke over the last few years, especially this year. And so that really kind of messed up our system for what we were doing. So we ended up having to develop a smoke mask as well. And from this, the original one, the smoke would be picked up over some terrestrial areas with the white here, but not over the water, which was very problematic for what we're trying to do. So with that, we the smoke mask, and then we ran all of our processes, and everything seemed to work out really well then, plus anomalies. So with that, we got good clear pixels. We can develop models. And the way we've been doing that is we take all available field measurements that we can find and link them up with all of the clear imagery, and then we can develop models for here we have second chlorophyll, and for second, this is just 2019. We had over 6,000 measurements within one day of the clear imagery. So it's a pretty good band set, data set where typically when you're calibrating each image, you'd have 100 and more recent years, maybe 300 measurements to calibrate it with. So quite a lot of data. With the 4 years, we have over 20,000 that we have completed so far. For chlorophyll, it's been about 3,500, and that is about over 12,000 with the 4-year data. So one thing I was talking about earlier with the ocean models versus the water, so they're using the blue-green versus using that red edge and the absorption trough. It really becomes clear when we have a few waters in Minnesota that are clearer than others. Use my mouse now. There it is. So if you look at this little really clear water, there's a kind of an offset of the linear trend here. And so right now we're working on a model. I have a undergrad student actually who's helping me and working on some correction for the chlorophyll, and we've got a good approach, and we'll be reprocessing all the data. So the nice processing, it's all set up. We've done all the hard work. We can test models, and we can apply new models to all the imagery really quickly. So that's where we'll be doing this after this October, when we'll have all of our imagery for 2001, and then we'll reprocess the whole archive and add that to the Lake browser and make it available to people. But having this, it's been so when we first started doing this, it was the main people doing water stuff were the ocean people, and it was always the trying to use the ocean models in inland waters, and it never worked because of the CDOM. So it was quite a battle with getting things published and things, because there was always the reviewers were all these oceanographer type folks. So now it's pretty well understood, and a lot of people are doing inland waters now. It's been quite a thing with the Sentinel-2. So with that, we have our models. We can apply it to all the imagery, make the data and maps available, and put it in our Lake browser, make it available for people to look at. So here's just the Sentinel-2, what the available imagery across the state. So for statewide, we have good coverage for the state. You can see there's a difference between the overlap areas. So that would be where the blue and the green dots are, and then this would be in between those areas. We go to the monthly period. What we found is it works pretty well to do monthly mosaics. So what we've been doing is we've been doing monthly mosaics at the pixel level, and then we compile all of the individual measurements in all the daily measurements in a spreadsheet, and then we can calculate any period we want for average or median or something. And that works fairly well. There's a few periods that are missing with the cloud or smoky imagery, as you can see for September, but for the most part, it works out fairly well, and it seems to be a way forward in a place like Minnesota, where it is fairly cloudy a lot of the time. So we can make our pixel level, lake level maps. We have chlorophyll, clarity, and CDOM available. And I'll just show you some examples here. This is Lake of the Woods rainy watershed. Let's see if here we go. So this is just 2019. We have this one little red dot shows up right here. I'm just going to show you that. So pretty much this area, Lake of the Woods and upper and the lower red are kind of known for having a lot going on in them with algal blooms and stuff. But for the most part, these areas are fairly pristine. If we go again, we can see there's a few areas that are a little bit lower, but this red dot kind of just popped out. And so I kind of investigated that further. Let's see. Nope. What am I doing? Okay. Yeah. There we go. And with that, I looked at the imagery, and yes, there was algal bloom on that. So it's kind of interesting that this way over 10,000 lakes in that area, and you're able to find one that has an issue going on. It looks pretty remote, so I'm not sure what was going on there. A few roads over there, so I'm not exactly sure, but there definitely was a bloom. 2020, same thing. Let's see. Get my mouse figured out here. Yep, there we go. So kind of a similar pattern. Fairly pristine area. Let's move on to more of a recreational lakes area, the Whitefish Chain. Well, you'll notice 2017, the data was fairly lacking. That is basically because the United States was in a ramp up stage. The Sentinel started in Europe and Africa first when it was first available, and they did, that was their kind of their primary target, and they'd hit a few images in the United States at that time. So you can see do it one more time with by the end of September, the imagery coverage is really good, and that continues through this day. So we have a nice data set for doing different studies with. There's a few lakes you can see that are kind of consistently a little bit more eutrophic than others in the system. A lot more exciting area is the Twin City metropolitan area again. Again, you can see the lack of imagery starting in early 2017. Oops. Let's see, here we go. Okay, so we're going to go clip through these areas. As you can see, there's a lot of blooms that kind of start in the late summer period in the agricultural areas around the cities, and some of the lakes up in metro area as well. That's kind of a consistent pattern that's going on. But a lot going on in these lakes. We have all this data, every lake for chlorophyll, clarity, and CDOM for 10,000, all available in the lake browser. Take a look at. We will have 2021 later this year. So now we also have the daily data available. So I'll just show you some examples of that. So we have this is Lake Francis in southern Minnesota, more of a mesotrophic lake. We have Tatanka, which also it's more of a eutrophic lake. And then we have Washington, Cicada, both eutrophic to leaning toward hyper-eutrophic, and German, and then Elysian, which is definitely a hyper-eutrophic lake. And these are all for Lake Washington, so you can kind of see the difference in the coverage for Lake Washington versus the others. Still quite a bit of coverage for the gray dots here as there is for the others. So it seems to give a pretty good data set that isn't available for any of these things. I have this for all these different years, and you can see how the 2019 and 2020 Elysian had a higher, more blooms than it did in the previous 2 years. We can compile that at the monthly level here. Oops. Let's figure it out yet. There we go. The map on the left, and then the graph showing the patterns for the different lakes. Okay. Do we want to do questions now, or should I wait till the end? I have the next talk I'm going to talk about spatial and temporal trends of the database, but if anyone has any questions on the first part, we could answer those, and then I'll move on to the rest of the presentation. That works.
Yeah, I don't see any questions in the chat as of right now.
Okay, so if anyone's got one, speak up. If not, I will continue. Okay, let's go on then. Okay, so basically I'm in the process of updating our geospatial and temporal analysis. We have the data through 2020, and for the long-term trends, basically I used the previous assessments that we've completed through 2015. And then I just basically calculated a late summer period for these years and included those in the analysis for trend analysis here. For distribution throughout the state, we have the northern lakes and forests. So I have some whisker plots here. Northern lakes and forests have some of the best water clarity in the state. Most of our lakes are up here too as well. The hardwood forest region, which is more of a transition zone between the lakes and forest wetlands up north and the agricultural area, so more of a mixed land use. It's kind of, you can see the land use, or the water quality is kind of mixed as well. And then we have the agricultural ecoregions, and those are lower water clarity in those. So we look at the long-term trends. So basically, I have looked at the trends of 10 TSI units or more. So it's doubling. So 10 TSI units would be equivalent to a doubling or halving of algal biomass. I use TSI units instead of like a measure of foot. So like if you had a 30-foot Secchi disc and you had a 1 foot difference, it's 31 or 29. It really doesn't make, it's really not normalized change. If you had a 2 foot Secchi disc and you went to 1 foot, it's a big difference. So, so by using TSI, that normalizes through the whole range of water clarity. About 13 had increasing water clarity. 5.7 had decreasing water clarity. We take a little smaller slice, 5 to 10 TSI units. We had about 18% increased and about 8% decreased water clarity. We look at the distribution through the state. The agricultural ecoregions with these pie charts, decreasing water clarity lakes than improving. And then let's see, for big thing that I kind of spot. I mean, there's a lot of improving areas in the metro area, and then you have a lot of decreasing out in this area. And then one thing that concerned me were these lakes up in northern Minnesota, the yellow ones here, which were decreasing more than I thought they should. When I investigate them, they are smaller, shallower water bodies that are decreasing the most. And so that's kind of led me to start looking into what's going on. First thing I did was look at the temperature and precipitation. And that's what I have down here. These are the time spots for our assessments at the bottom. But you can see big increase in temperature over this period, 2.6 degrees Fahrenheit. This is late summer, August, which links up with the water clarity data that we have calculated. And then precipitation also seems to be a little bit higher, larger swings in the precipitation rate for these years. So all could be contributing. Let's see. The other thing I started looking at was land cover stuff, and it was the LC map product just came out. They currently, I think they have it through 2019 now, 2020. I'm going to redo this this assessment again when the 2020 becomes available, so I can kind of match up the two data sets to have consistent land cover and water quality data. This is a preliminary assessment, 1985 to 2018. And basically what I did is I calculated the pixel level change from and to classification at the pixel level, and then compile that at the catchment level, which is over the right. So some parts of the state have seen a lot of change, up to 54% in some of these areas, metro, and then some of the forested areas up here. We identify what they're going to. This is harvested forest in this area, and then this is regenerating forest over here. And if we go to treated cropland, there's a few areas that are actually doing, kind of converting forest into cropland, irrigated cropland, and that's kind of a problem. And a few of these areas have been concerned for lots of researchers and agency folks. And let's see, oops, I keep doing that. Look at the areas that are being developed, a lot of the cities, and then the metro area, of course. The mine, and the mining activities up in the Iron Range, and then to cropland there. There's lots of areas that are actually, areas that have been harvested and regenerated, but other areas that are kind of filling in around the metro. It seems like a lot more trees are growing. Must be away from agriculture in some of those areas as it gets developed. And then water. There's a lot more water. These areas where a lot of those changes were out in this part of the state. And then wetlands there. So look at some gifts of some of these changes. This is up in northern Minnesota, and you'll see the white-eaten areas are the areas that are being harvested in there. So there's a lot more harvesting going on in these areas than there was in the past. Let's go to the next one. This is Hubbard and Wadena County. And you see some of the forest area turning into cropland in some of these areas. And the last one is the Prairie Pothole region, western Minnesota, and you'll see a lot of these areas filling up with water. So there's a lot of the prairie potholes are filling up. So kind of a wet period for part of this time here. Might have got corrected for this year with the big droughts. So this is where the temperature data came from from the DNR. Here we have precipitation change. So we have basically more precipitation in the southeastern Minnesota than northwestern Minnesota, and the change a lot drier up north than there was earlier periods. And then for heat, for temperature, basically warmer in southern Minnesota, cooler up in the Arrowhead. But if you look at where it's changing the most, northern Minnesota is changing the most actually in the whole country. So big concern there, and we will be seeing some effects from that. And here again is the graph that shows that increase. Another thing that's changing is the type of crops that are being planted. And so here we go from the total cropland actually is going down, probably due to development in the metro area. But corn and soybeans are actually increasing considerably over this period, where the small grains and other are decreasing. And you can see the same thing in this chart over here, where now it's getting to be mostly where it's about half and half. Now it's the large majority is corn and soybeans. Here we have corn, and where it's increasing a lot out in the western, where a lot of that decrease of water clarity has been. and then or western, and then southeastern Minnesota. Soybeans, a lot of soybeans being planted up in this area now, where it really wasn't before. I was up in Lake of the Woods doing some water sampling, and basically we saw corn growing up there, which never used to be really the case. Small grains, basically decreasing in this whole area. Western Minnesota. The other crops decreasing in a lot of the areas as well. And then animal units, a big increase in central Minnesota. Let's see, where do I got my mouse there? Central Minnesota, western Minnesota. So to try to start making a little sense out of all this, I did a spatial and temporal trend analysis, linked all the water quality data to headwater catchments. So this is just the headwater catchments, the ones that would be considered the lake watershed. And then I basically started with the 2015 because that was what was available at the time, and I matched up with our older data set. And so just started looking at this to see what kind of features would come out as for different impacts to this. Used random forest, which is a powerful state-of-the-art approach for data analysis. It's an ensemble learning method, operates on multiple decision trees, and where each tree is grown partially on random, either subsample of the trained data or subsampling of the available features. And so it allows you to put whatever you want in there, and then it kind of identifies the important variables and uses those for the models. So when I look at that, I separated all the lakes out by shallow, medium, and deep. And I'll show you in a second why that matters, but you can see here it is. So it's basically shallow, medium, and deep. Deep lakes tend to be a lot clearer than shallow waters. If we look at cropland, more cropland, the lower the water clarity, but that pattern, that pattern consists for each of these, but the deeper always clearer than the shallow waters. So it's a good idea to separate them out when you're doing an analysis with it. Developed, used to be a lot more, the last time we did this was a lot more of a signal for the developed areas, but I think with a lot of the BMPs that are being done for development these days, it seems like it's kind of helped with improving the water quality in some of these regions. Tree cover, if you have in forested areas, is always good for water quality, and so forested areas tend to have a lot better water quality than agricultural developed areas. So just starting to look at random forests. This is just a work in progress, but just kind of looking at decreasing water clarity lakes and things that the water tended to be a big factor, in areas that were showing up. So the bars kind of indicate the ones that have the most impact. And when they're getting that wetting area for the prairie potholes, tend to be a lot of those decreasing water clarity lakes. So that's probably part of it in here. Be interesting to see when I get the 20 data to see how that matches up. So I can't even see what we got here. So the change here, the increase in water clarity is more developed. It seems like the developed areas actually, and I've seen this at other studies across the country, is basically developed areas seem to improve water quality because of the BMPs, which is good. I guess we're starting to do things right. That thing, looking at shallow, medium, and deep lakes, I'm just going to go right to putting some things. This is basically the difference between, the deep lakes act differently than the shallow, but the things, a lot of the hydrologic and climatic changes are important, as well as more the land use intensification factors. Both are kind of interacting to impact our waters, and trying to figure out exactly what's going on is challenging exercise. So here we have going from developed. So here we have developed land use, and what we see is as the areas get developed, or developed areas are actually improving water quality over this period of time. Or wait, no, this is different. Okay, no, that's all right. So basically, the more it's developed, the better the water quality is in this area for the percent. The developed area change to developed, also increasing clarity with the higher percentage of development. If we go to cropland, decrease in water clarity over the period, and then a bit of a decrease in changing the cropland as well. And grass and shrub, changing the grass and shrubs, so those would be areas that were just harvested, decreasing in those areas. The temperature didn't have as big of an effect as I thought it would be, but the changing temperature has a little bit of effect in the decreasing water clarity, but not as much as I would have thought. I think precipitation actually seemed to have a bigger effect in temperature. Let's see, this is the, let's see if I can even, let's see. I don't even see what I can't even read what slide I have here. I don't remember which one this one is. So I'm just gonna go skip through these. So okay, so let's go to okay, so we have done some geospatial analysis. I'm going to be updating that with the 2020 data and finishing up a manuscript on that coming up here. I'm going to go to show off our lake browser here. Let's see. So get this up there.
You might have screen sharing set up to only, oh, never mind. There we go.
Okay, so we have, I just edited another screen for a while. Okay, so we have just updated the lake browser a few months ago to have this new data set. So we have the lake level data, and then we have pixel level data. So we can pick the different things there. You can pick different months. So you can have the summer average, or you could, you can't do it for pixel level, but you can do it for the, oops. So you can pick different months to see what's going on in the areas. You can zoom into different areas. Let's see, we can zoom into like the St. Louis River estuary. You can see plumes coming into the Lake Superior. Different times of the year. We can have, see some of the CDOM. There's another big thing that's kind of interesting in some of these areas. You can see the CDOM. You can see, sometimes you can see the plumes coming in into the system here. See where there's a change in it. I think, let's see if I can find that period. Like here, I think, yeah. So you can see it's fairly low and rainy, but then you get a big, from this river here, you're picking up a lot of CDOM into the system from this bunch of wetlands out in these areas. So you can actually change the background to do it to see all the wetlands in the area. Imagery. So we got lots of options here for that. Zoom out again. To southern Minnesota, and then we're going to change back to change the clarity, I think. Okay, so from any lake, so all this data is here at the pixel level or the lake level. And then you can pick different lakes. You can pick any lake and you get a report of that lake. So this is, so you have a trend. So you have the trend. This has been getting clear over the years. And then from there, you can get a seasonal, what are the trends for that, for clarity. This is the clarity over the summer, and starts out a little bit clearer and gets a little bit more less clear. We have all the monthly data. We have the seasonal data for the early stuff, and then once we got the new system for the newer imagery, we have the monthly data, and we also have the daily data here. So you can actually click this. Now every measurement that was collected for that lake is here, and quite a few of them for this period. And then we get down here, we have percentile. So basically we took, it was the average summer, June through September, 2018 through 2020, when there was lots of imagery available. And then we ranked all of the lakes. So for this one, statewide, this is clearer than 4% of the lakes. For Hennepin County, 87 and so on. The chlorophyll trends basically starts out a little bit higher, gets lower in July, and then it increases later in the season. And oops, what did I do? And for CDOM, just minor changes here. We also have land cover data in there. So that is all in a report for all these lakes. There's a great data set, which will be updated in sometime later this year. And let's see, there are some questions. So I'm ready to take questions. I think, let me see, let me go. Oh, I got, let's go. I got a couple more slides I'll go through and then we can take questions. So we're starting to we've validated in a few other areas, like Wisconsin and the Dakotas. We've been looking at some of the reservoir systems down in southern states and Alabama and Georgia. Much more dynamic systems and a lot clearer down there. So there's a lot more clear imagery, which is pretty neat to have. And then I showed you some of this stuff. We're also looking at calculating greenhouse gas emissions and societal cost with John Downing, University of Minnesota, Duluth. He's stationed up in Duluth, and then Stefan Newbold from University of Wyoming. Some of the why do we care about water quality for the greenhouse gases? The large, basically for the greenhouse gas emissions, a lot in the agricultural areas. If we look at societal costs, some of these larger lakes have a big impact because they're so large, but also a lot of the agricultural lakes also have a big impact as well, even though they're fairly small. Also looking at forecasting, what's the next step of doing this? Looking at actually forecasting chlorophyll levels. The big thing with the remote sensing, you cannot really rely on a satellite image collecting clear imagery, and so you really need to figure out what's going on. But with the data that is collected, you have a system where you can actually determine some good idea of what lakes are having blooms, what temperature they are when they are having these blooms, and calculating, at this temperature, this time of year, we'd expect algal bloom, so you can do a probability for a bloom. So that's one of the things we're looking at, and also doing this system, similar thing with turbidity plumes in the reservoirs. If you have a storm event, you could predict when a turbidity plume would be in different parts of the reservoir system. With that, I will take any questions. You want to read them off, Chris, or what's the best way to do it?
Yeah, for sure. So it looks like some of these questions are focused on kind of like data availability. Are these layers available in ArcGIS online, and what's the kind of best way to download this water quality trend data from Lake Browser?
I'm not sure if we have that. We used to have that capability in the system. I'm not sure if we got that put back into it or not. but you used to be able to download it from there, and I haven't checked that capability really. So they can email me if they want to work with the data set or something.
Sounds good. I will get in touch with you about that. So Dr. Phelps asked, what does the future look like for satellite technology and data processing? How much more real-time and finer resolution can we get with our remote sensing?
Well, okay, so for right now, the big change has been the European satellites have added that red edge band since the Maris satellite. So it's been quite a while. The US has been slow to add the new spectral bands to the sensors at the moderate resolution. There's a hyperspectral PACE mission, but that's a ocean satellite, so it's a 1 kilometer pixels. So there's the big next advance for the US will be Landsat Next, which is probably 2028, I think it is. And so that'll that they actually with the Landsat 9, which is going to be launched on Monday. I was at one of the NASA conferences back probably 5 years ago when they're designing it, and asked about the red edge, and it was like they how could you expect such things on the technology? They were really set on keeping consistency through keeping the 70s technology into the future, and they weren't open to new ideas. Now they are definitely open to new ideas. They met with a lot of us researchers and what spectral characteristics would be useful. So agricultural community, water community, a bunch of communities. So they're basically Landsat Next should be a well-designed multispectral satellite with all the right bands. And so it'll be really good for water. It'll be really good for agriculture. It'll be really good for lots of things, but that's not till 2028. So we have to wait a little while for that. But for the red edge, I think it's just, it's new, recent, the last few years. And so that is a real game changer right now. So I think we take advantage of that until we have some better stuff coming down the road. But the image processing stuff, back 20 years ago, processing this amount of data would be pretty much impossible, especially for the local researchers. Now with the supercomputers and Google Earth Engine, this type of processing can be done fairly quickly. Still have to do the hard work of actually doing the proper image processing techniques, which is sometimes missed in some of the different techniques that are used. So hopefully that answered your question.
Yeah, nice. I had a personal question. So I have noticed that like in more oceanography kind of remote sensing, there's kind of like a lot of stoichiometry, like kind of linking, I don't know, carbon to nitrogen or phosphorus. Have you guys ever thought about that, or do you know of any people doing that in freshwater?
Usually, where would you get the nitrogen and phosphorus from? So you can't, I mean, you can optical variables, so you can't measure with remote sensing.
Right. So like, there's kind of like, I don't know, the idea that, there's a consistent kind of stoichiometric ratio between carbon, nitrogen, and phosphorus.
Okay.
And so like, if you can get carbon, you can get to nitrogen and phosphorus that way.
Yeah. Well, let's talk. We can set it up. I don't know if any studies are doing that, but that's probably a good idea.
Cool. Well, I have another question then as well. I've seen some like kind of lake ice, I guess like characterizing and making like these long-term data sets using remote sensing with lake ice.
Yes.
I was, just curious. So I know, there's a huge citizen monitoring program with PCA and DNR about lake ice. Have you guys ever thought about doing any kind of like lake ice remote sensing kind of stuff?
Yeah, we have the Sentinel-1 is a SAR, so it's a synthetic aperture radar. So we've been looking at that, combining that with the optical data, and you know, the big thing with the SAR data, it sees through the clouds, and so I do have some pretty cool, you know, GIFs showing. If you go to my Twitter page, like you can see some probably way back, late, you know, quite a few tweets ago, but we have GIFs showing how lake comes on and goes off of the lakes, which is very interesting actually, and it's been a big interest of ours, and we've put in a couple of proposals and they haven't gotten any funding for it yet, so hopefully it'll be funded, because there definitely is a potential. We're doing another NSF proposal here, should be coming out, and we're putting getting it finished up the next couple months, so hopefully that will get funded. But that was tied with ice limnology with some folks up in Duluth, and so that's a lot of interest in doing that type of work, because there's lots of interest and some cool stuff.
For sure, that sounds super cool.
Should we have some pictures? Yeah, look on our Twitter. Say, I don't know if I have any of those pictures, but they are pretty cool. Time's up, I guess. Another time I can send them to you.
Yeah, that'd be awesome. So yeah, if there's any other questions, feel free to shout them out. Otherwise, we have another seminar, same time next week, with Dr. Eric Larson from the University of Illinois, Champaign-Urbana, and he will be talking about environmental DNA.